start. First, I want to say, because it's not so optimal here in this room and in the neighboring room, also for the for taking the video, we've now got, at least for one of the days, for Friday, we got a lecture hall. So on Friday, from this Friday on, we will be in the Part 12, H12, over there. Okay, so let's start. What we developed the finite element method for the specific case of the Poisson equation with homogeneous Dirichlet boundary conditions, and we saw in general what the Galerkin-Ansatz means, namely solving the variational equation not on the full function space but only on a finite dimensional space, means to solve a set of linear equations. In general, that means independent of the underlying problem of the underlying bilinear form and linear form for the right-hand side, independent of the basic space V and independent of the ansatz space VH. In all those cases, if we choose a basis phi 1 to phi m of the ansatz space, we see that due to the bilinear nature of the form here, the requirement that we are looking for a solution UH from VH such that the variational inequality holds true for all test functions from VH. This is equivalent to this set of equations where the system matrix, the so-called stiffness matrix, comes to existence by inserting the basis functions in the bilinear form. The ijth element is a phi j phi I, so just the other way around. And the right-hand side is just the evaluation of the functional of the right-hand side of the basis function phi I. So it's now clear what the basic things to do is. First is the assembly phase, that means to set up the set of equations, and the second is, of course, to solve the set of equations. And on the other hand, if we do exactly the same thing for the Ritz approach, where we know already that, not in the general case, this was a very general consideration. For example, it did not need the symmetry of the bilinear form. So the Galerkin approach also makes sense if the bilinear form is not symmetric. That is not the case for the Ritz approach, but if we have this asymmetry in addition, then we know these two approaches are equivalent. And positiveness we also need, not really definiteness, but positiveness of the bilinear form. And if we, they are equivalent on V, but they're equally equivalent then on VH, they're equivalent on any space where they are defined, of course also then on a finite dimensional one. And that means we have the same thing here in the finite dimensional setting. If we work out what this finite dimensional minimization problem is, it turns out by exactly the same consideration that it gets this quadratic form, again with this already defined matrix AH as the matrix defining the quadratic part, and the vector QH in defining the linear part. So what we see here, again, is the equivalency of the set of equations and of the minimization problems. That is, of course, not true for any set of equations, but for you might know that it's true for symmetric positive definite matrices, and that is also the background here. So if we now look a little bit at the properties of this matrix AH, we can see several properties. The first thing what we see, if the underlying bilinear form is symmetric, that is the case in our example. That might not be the case in more general examples. If convection is present, then this is not the case anymore. Then also the matrix is symmetric, because the matrix is just A phi j phi I. So if A is symmetric, of course, the matrix is symmetric. The other thing is, if the form is positive definite, if the form is definite, then also the matrix is positive definite. So this is just this framework where we have the equivalency basically the framework with the equivalency of the two formulations, Ritz and Galerkin, and therefore we also have then the equivalency of set of equations to solve and minimization problem to solve. Why is this matrix positive definite? So we just reverse all our calculations what we did. So we take some vector, some tuple vector xi here, and correspondingly we have the element of the function space, which is the linear combinations out of these coefficients and the basis vectors. We just have some fixed basis, any basis, in a general situation. This is a consideration of general situation. So we write down what this quadratic part of the bilinear form means. This is this thing here. And now we just reverse our old computations. Now we bring in the coefficients and we bring in the sums, first with the right component of the bilinear form, then with the left component, and then we see we have the bilinear form evaluated at the same element, left and right, namely at the element u. So in any case we know this is greater or equal to 0, and it's greater 0 under the assumption of definiteness if the function u is not 0. But the function u is not 0 if and only if the vector xi is not 0, as we are dealing here with a basis. And this gives us the positive definiteness. And up till now we only have said, okay, those two problems are equivalent, independent whether they have 1, 0 or 5,000 solutions. Now we know under these additional assumptions, namely on the assumption symmetric positive definite, or better definite bilinear form and linear form on the right hand side, we know that there's a unique solution for both versions. Because now the matrix is positive definite, therefore the solution of the set of equations is uniquely existing, and the same as its equivalent applies then to the minimization problem. So, and later on, of course, so what we want to do or have to do later on, we have to give up this requirement of symmetry. Symmetry would confine us only to diffusive processes. In the moment where we have additional advective processes, we lose the symmetry. And in the near future, one of the next steps will be to extend the theoretical framework such that we can be sure that both on the continuous and then also on the discrete level, also in the non-symmetric cases, solutions exist uniquely. So now, before doing that, let's first have a look at the matrix which comes out. What are properties of the matrix? And the most important property of the matrix, and that is what is the reason for choosing this specific ansatz functions in the finite element method, and that is what defines a finite element method beyond a general Galerkin method. I said a Galerkin method is an old thing. Galerkin did these things already in the late 19th century by some hand computations, but he had other ansatz functions because he did hand computations, and he never was so ambitious as we are now to have 1,000 or 10,000 or 100,000 degrees of freedom. It was at that time, of course, totally impossible, and it's now possible because our ansatz function have a very special properties. Namely, it leads to a matrix with is sparsely populated, dünn besetzt. That means that we will later make this notion a little bit more precise. It means most of the entries of the matrix are 0. And of course, we then will and have to take advantage of that in the solution procedure, and that is also the reason why we are able to solve such large sets of equations. Yeah, why is this so? Okay, what does it mean? So the entry is non-zero, of course, by definition, if this integral does not vanish. Such that this integral does not vanish, of course, a necessary condition is that the support of the one function of the gradient of phi j and the support of the gradient phi I have something in common. Otherwise, we would integrate over the 0. It is easy to see that the intersection of the support of the gradients is contained in the intersection of the support of the functions. Because if a function is 0 and an open set, of course also the gradient must be 0 there. That means, what does that mean? It means a necessary requirement to have a non-zero entry means that the supports of the two basis functions have to have something in common. They have to have a non-zero intersection, a non-vanishing intersection. Okay, this was now general. Now we have to look a little bit on our specific basis function. And then we see, for example, if we would have taken global polynomial space, then our basis function would be the monomials, x, x squared, x to the 3, and the same for y, and the mixed terms. And all these functions, they only vanish on quite a few points. That means this would be a much too strong requirement, and we would, according to this consideration, in this case, end up with a matrix, with a full matrix, with a matrix which has entries everywhere. But now we have our piecewise defined, piecewise linearly defined continuous functions, and in each of the elements the function is a linear function, and now the situation is different. Let's now go specifically to our nodal basis functions in the specific case of the element space we have defined. That means we have a function which is 1 here, which is 0 on all those neighboring nodes, and of course on all the other nodes. Due to the uniqueness of the solution of the interpolation problem, first of all, we know in all those elements where all degrees of freedom are prescribed with 0, then this basis function can only be identically 0. So the only place, the only region where the function can be non-zero is this area, is the union of all the triangles which have this node as a vertex. And of course this number depends on the specific triangulation we are using. But later on we will have requirements which ensure that also if we do a refinement process, this number will be bounded from above. So it will not be possible that for one h we have here 10, and then for a smaller h we have 100, and then 1,000. Such a spider web structure is not good, and this will be not allowed. So this is basically a fixed amount of triangles which meet here in such a point. Okay, now what does that mean? We want to have a non-zero intersection. So what possible other basis functions are candidates? Only those which belong to these neighboring nodes, because they are the ones which then have an element which lies both in the support of phi 1 and phi j. So in this specific situation, that would mean in this line, in this line, in this row of our set of equations, okay, there's of course an entry at the diagonal point. This comes from here. This comes from the coming together of phi 1, of gradient phi I with gradient phi I. And then we have possibly further entries from those neighbors. So in this case 1, 2, 3, 4, 5, 6, 7, if I have not miscounted. So in total we would have 8 entries here in the corresponding row, irrespective how big the whole discretization is here. If we have 10,000 nodes or 1,000,000 nodes, or who cares? So we see again this sparse structure which we have seen already with the finite difference method. In the finite difference method, everything was very well ordered by our stencils, and there we saw in the finite difference case with our standard stencil we had 1 plus 4, or at most 4. So this is again noted here. So that is what we have now concluded. If the entry is non-zero, then necessarily the corresponding two nodes have to belong to one common element. That's the situation for our specific element, and the only thing which plays a role for this consideration is that we have the degrees of freedom in the nodal points. Okay. Basically, I've said this already. Now let's look at a very specific example, also to see the connection to the finite difference method, what we are doing here. So again, our model problem, and now we also take the model domain, namely the rectangle, that we can relate to the finite difference method. And this rectangle is subdivided into triangles into a specific way, namely correspondingly to the definition of the grid points in the finite difference method. We subdivide first in squares with length h, and then we subdivide the squares again in two triangles, either in this way or in this way. It will turn out that the discretization which comes out from both of these choices is the same. Okay, so what does that mean? If we look at such an interior point like this one here, right? It's very coarse discretization. You see there are no points which are far from the boundary. If I now look at the stencil, I'm always in the boundary. But okay, let's ignore the boundary conditions for a moment. Well, how many neighboring points do we have? Okay, we have the 4 here, which we know already from the stencil. And then we have additionally this one and this one. So we have at most 6 neighboring points. That would tell us we would have at most 7 entries in one row. Okay, let's try to compute these entries. Let's first have a look why these formulations are the same. So we look at this, we pick a node, and we look at all the elements which have this node in common. So this gives us a picture like this here. In the one case and in the other case like this. So one thing, this indicates what ingredients for the integrals we have to compute. Now if you compare this situation with this situation, you see that we can transform one into the other if we just flip around. If we just keep the y variable as it is and substitute the x variable by a minus x, then this situation transforms to this situation. But if you look at our equation, what happens with the equation, both in the classical formulation and consequently then also in the weak formulation, if we do such a linear transformation, we are dealing with second derivatives, it doesn't change anything. So we do not change by this transformation, we do not change our problem if the boundary conditions are correspondingly that the left-hand side boundary and the right-hand side boundary are also the same, which is the case here as we first only dealing with homogeneous sterically boundary conditions. So we get in both situations, we get the same discretization, and so let's compute the discretization in this case. So to facilitate this a little bit, I have introduced here a sort of a local numbering. I call the reference point AZ, like Zentrum. So this is still, the indices are German. And then we have here east, west, north, south, southeast, northwest. And then we need some numbering of the elements involved. These are 6 elements, and I go in the counterclockwise sense, go through by Roman 1 to Roman 6. Okay, so now let us compute. Unfortunately, I cannot have here 2 screens. So let us now compute the entries of the matrix, and let's, by computing the entries for this row, which corresponds to the index Z, and let's start with a diagonal entry. So what does that mean? For the diagonal entry, we have to compute A phi z. This is gradient of phi z scalar product with itself, so Euclidean norm squared. We have to integrate that, and we only have to integrate over the support, that is over the 6 elements. So now our ansatz functions are piecewise constant, piecewise linears, that is, the gradients are piecewise constants on the elements. So we just have to compute the gradients, the partial derivatives of our ansatz function here, in this case of phi z, on these 6 elements. And this table gives us the values. Maybe we check this, not all the values, but some of them. And then you can compare whether this table is the same thing what I'm now going to say. Hopefully I say the right thing. So let's first, for example, look at the element 1. We know here we have a 1 at a set, here we have a 0, here we have a 0. So the y derivative is then minus 1 over h, because we decrease from 1 to 0 over a distance of h. Correspondingly, we have here also 1 over h. For example, this element, on this element, what do we have? We have here a 1 and a 0, nothing changes. And here we have a 0 and a 0, so correspondingly the y derivative is 0. And this gives then, so I've computed these 4 values right now, and this gives this full table. And now what we see is, what we do, we look at this vector, we're only interested in Euclidean norms, so the signs do not play a role. And in this sense, the element 1 corresponds to the element 4, 2 to 5, 3 to 6. And that means the integration can be reduced to the integration over the first 3 elements and multiply the result by 2. So we only have to have this number here. So what do we get? So we go over these 3 elements, and we always have to add up the squares here and multiply the thing with 2. So we get then 4 times 1 over h squared times 2. And now we have still to multiply with the size of our integration domain. What is this? This is an element. This is 3 times a triangle, and each triangle has the volume, has the area h squared half. So we get here. This is again a little bit more in detail. Let's do it in this way. So here we have 2 triangles. So we have an h squared. We have a 2. We have the 1 over h squared here from the integrand, and here the same thing in the other part. So we just get a 4. And this 4 should be sort of familiar to us. Okay. Now we do the same thing for the other entries. And I only indicate a little bit the computation, do not everything in detail. For example, if we want to compute the entry Zn. So what does that mean? We have to look at a phi n phi z. That means we have here the gradients of phi n and phi z. Now we need the intersection of the support of these 2 basis functions of z and of n, and these are these 2 elements which have these 2 nodes in common, the element 1 and the element 2. And if you now look, so to speak, look at this picture, so to speak, through the eyes of an, then you see that 1 and 2 for an, of course, not the full support is depicted here. Only two of the 6 elements are depicted. But these 2 elements depicted here for an play the same roles as the elements 5 and 4 for AZ. They are just the ones which sit below here. And from that we can conclude what the derivatives are there without doing everything again. I go through it now a little bit more quickly. And oops, here we are. So we only have to go over these two elements, and we see in each of these two elements, one of the first derivative vanishes, so we only have to deal with the second derivatives. The second derivatives bring in 1 over h as the integrand, and the volume about which we are integrating is 2 times a triangle. This is a misprint here. It should be just an h here. Brings 2 times. No, sorry. That's wrong what I said. Okay, so we only have the second derivative. These are the values of the second derivatives. So I get minus 1 over h squared, and then have to multiply it with the area. This is h squared, so I get a minus 1. Okay, so the story goes on. So if we get for north, south, east, west, we get a minus 1. Surprise, surprise, so to speak. But there are still the north, what was it? There are still possibly, so analogously we get these 3 values, but there are still possibly, what did we say, the northwest value and the southeast value. Is there something or is there nothing? So we just have to compute these things, and I make it a little bit short. It goes according to the same line. For the northwest entry, we get a 0, so there are contributions. If I only look at one element, I get contributions, but the contributions cancel. The argument, the necessary conditions, what we said, okay, if I look at an element, if there cannot be a contribution, of course there cannot be a global, from any element, there cannot be a global contribution to this entry. But it might well be that there are non-zero contributions from different elements, which in the end cancel. And that happens here. These 2 contributions are non-zero, but they cancel in the end. And correspondingly also for southeast value, so in the end we really have only 5 entries here per row, not 7. And you have recognized it, of course, the entries are exactly those entries from the 5-point stencil. Okay, so what we did here, which is not typical for the finite element method, and we will, I think today or tomorrow, we will discuss the common alternative approach. What we did here, we did a node-based assembly procedure. So we went through all the nodes and correspondingly computed, so to speak, in the nodal indexing of the matrix, computed the entries of the matrix. What we will later do is a so-called element-based assembly procedure. So this was only here for convenience to deal with this example. It's not the for the general way, it's not the proper way to do that. So we have seen, we get here basically, if we look at the finite difference discretization and take there the row-wise lexicographic numbering, we get the same stencil. There we have still the factor 1 over h squared. So we have to see where this factor 1 over h squared is. So let's have a look at the right-hand side. What do we have to do there at the right-hand side? Here we have to, what is done here, we multiply the whole thing with 1 over h squared to get, for the matrix, to get exactly the matrix we have for the finite difference method, and then the right-hand side term is 1 over h squared times the integral of f times the phi. We can again here restrict ourselves to the support of the basis function phi, that is to these 6 elements. But still there is now a problem here. Okay, if the f is constant, we can compute this integral. Similarly, as we have computed integrals over the gradient of the phi's, which was particularly simple because they were piecewise constants, we can also compute integrals over the phi's, which are linears. It could also compute integrals over some polynomials or some other special functions. So there are a lot, or there are some, depending how you would like to see that, f's for which you can compute exactly these contributions. But of course there are other f's for which you cannot. So to have a general method, what we have to include is an approximation of this integral here. So what we do here for the first term is what is called a variational crime. Yeah, that's really the notion, a variational crime. So we do not do, so to speak, the exact finite element method, but we change it a little bit. H-dependent, of course, and the theory, of course, in the end of the day has to deal also with this variation. It also has to show that if you do the variation like this, then your convergence result, or better, your order of convergence result is not changed by this. So what do we do? The only chance what we can have in general is to compute this integral approximatively. So we have to use a quadrature rule. And I assume that you all know something about quadrature rules in one dimension. From your introductory numerics course, you know something like the Newton's codes formula. And you know something like, possibly like the composed Newton's codes formula. And we do something like this here in a very simple case. So what would you do in 1D, for example? In 1D there is the composed trapezoidal rule. What does that mean? That means I have an interval, I have some function on this interval, and I would like to approximate the integral. What I do is I subdivide this interval in small intervals, and in each interval I substitute the integrand by its linear interpolant. I need those values here, I have to evaluate. Now I substitute by the linear interpolant. It might be quite good in some parts of the function. In other parts it's maybe not as good. And then I compute the integral of this interpolant. And that is my approximate value. So a quadrature rule is nothing but a linear combination of values of the function. And those numbers with which we multiply in this linear combination, they are called the quadrature weights. Quadraturgewichte. And that thing, we do the same thing now in 2D, or can do it in general dimension, and we follow the same idea. The idea was here to do an interpolant from some polynomial space and then compute the integral of this polynomial exactly. And here, what do we have on a triangle? We have the three nodes and the three nodal values. And of course, it's now quite obvious what to do, namely to use the linear interpolant of these three values and to compute the integral. And in this way, we get also a trapezoidal rule, Trapezoidal, now in 2D. That means on a triangle, we substitute the integral, that's the approximation formula, by the three values at the nodal points, and each of them is multiplied by 1/3 times the volume of k. That comes out if we integrate the corresponding basis functions from the linears. So this is on one triangle. What does that mean, for example, in our case with for a specific integrand, which has this right-hand side f and the basis function phi, for example, on the element 1. Okay, we have the 1/3. The volume is here now, in our case, 1/2 h squared for the volume for the area of the triangle. And now we get the three values, and you see only at one of those 3 points the basis function is 1, so only the central point gives a contribution. So we only get the function at the central point with the weight then 1 over 6h squared. Okay, now we have 6 elements times 6. Now we multiply with 1 over h squared. So by this approximation we again get the evaluation of the right-hand side at the corresponding point. That is what we did naively, so to speak, in the finite difference method. So we get the finite difference method back in this specific situation. That means specific not only linear elements and so on, but also this so-called Friedrich-Skeller triangulation. On another triangulation we would get something different. You can think of all nice kinds of triangulations, and they will lead to different discretization. For example, what is it? This thing here you can do. I think this is called the Union Jack triangulation. And you would get something different. Okay, so we get it back, but we have on the right-hand side, we have to use a quadrature rule independent from the problem that otherwise we might not even be able to compute the integrals, based on the trapezoidal rule. So we put this together to a statement saying here the finite element method with linear finite elements on a triangulation as in figure und so weiter. That means as with the Friedrich-Skeller triangulation and the trapezoidal rule to approximate the right side gives the same discretization as the finite difference. Okay, this shows a lot of things. That shows that maybe one can now see differently. You can say, okay, go away with these strange finite elements. They don't give anything new compared with the finite difference method. That would be one point of view, which I do not support. Another point of view would be to say, okay, we had all kinds of problems in analyzing the finite difference method, but maybe this has something to do the way we have derived the scheme. Maybe the scheme is not as bad. And this is now, so to speak, the right framework to analyze this scheme. So if I would have the chance, so if I have to solve a problem on a rectangle, usually one does not really in real life solve problems on rectangles, but anyway, or on cubes or whatsoever. If I have to do that, if my material is also homogeneous, which also is never the case, but if it is, nothing is bad with a discretization which is as uniform as the Friedrich-Skeller discretization. It's not that just to be fancy, if I have something like that here, I say, okay, but now I can do finite elements, so, but that means, of course, that I have a triangulation of this type here, and that's much, much better than the other one. In general, it will not be better because the more uniformity and symmetry and things he can bring into a structure, the more it will help me, of course. But of course, if my domain is not like that, but it's like that, then of course I'm forced to use such a non-structured triangulation, unstrukturierte Triangulierung, as one is called this. Okay.
Habe ich Sie kurz unterbrechen?
Ach so, Mikrofon. Okay, so good. This we have mentioned already several times. In the symmetric positive case, the Galerkin and Ritz method lead to the same approximations. And okay, now before going further with the finite element methods, let's see what is specific. So let's look at other Galerkin or possibly Ritz approaches which are not finite element approaches. And one I've mentioned already, what I could do, for example, if we look at our boundary value problem, let's say this is what we not really know till now. Let's say we look at a situation where we're not forced to enforce the boundary condition via the ansatz space. And this will be the case for mixed boundary conditions. So we are free in choosing our ansatz space independent of the boundary condition. Then, of course, as I said already, then it would be quite a reasonable choice just to take those polynomial ansatz functions here. But that has two consequences. The first is, as I said already, now the matrix is fully populated. That's a big disadvantage. And further on, it's a very bad matrix in the sense that it's very, very badly conditioned. You might know this in 1D. If you do similar things in 1D, you end up with a Hilbert matrix, so-called Hilbert matrix. And that is a typical example for a badly conditioned matrix. We could also do something different. We could say, okay, we take as a basis functions, we choose functions which fulfill this equation here. And you see here, you recognize hopefully here again an eigenvalue problem. So we're looking for non-zero functions phi, elements phi of the vector space, such that a phi v equals lambda I phi v. This is, if we would have matrices here, so if it would be finite dimensional, here would be just a matrix times phi, and here would be lambda times a specific matrix times phi. So that is what is called the generalized eigenvalue problem. If this matrix on the right-hand side is the identity, then it's what you are used to call eigenvalues and eigenvectors. And here in this situation, it's just the weak formulation of the eigenvalue problems here for our underlying differential operator, in this case for the Laplacian. So we formulate, as you are used to do that, for matrices an eigenvalue problem now for the differential operator. So we're looking for a non-zero solution which has where minus Laplacian of u equals lambda of u. This, so to speak, substitutes the au equals lambda u. And of course, we have our boundary conditions here. And if you now do again a weak formulation in the way we discussed that, you get here our bilinear form, and here you get the underlying L2 scalar product here. Now this is an infinite dimensional problem, so it's not so clear whether those eigenvalues exist and which properties they have and how to compute that. For example, in this situation, it can be assured that there is an infinitely a countable set of eigenvalues which has minimal, they are all non-negative. The minimal one is positive, and they only have an accumulation point at infinity. And they are all simple eigenvalues. That is, we can choose our eigenfunctions such that they are orthonormal with respect to the L2 scalar product. That not yet has computed us those eigenfunctions, but one could, let's say we are in a very special situation, let's say on the rectangle, where we really can analytically compute those eigenvalues and eigenfunctions. If this is the case, we are in a very, very good situation. Then we could say, okay, we take those eigenfunctions, not all of them, but the first n, to be the basis of the n-dimensional ansatz space VH. Now the H is not really visible anymore as a discretization parameter. It plays the role as 1 over n, where we cut off the sequence of eigenfunctions. What does that mean now for our problem to be solved? How does this matrix look like here, our stiffness matrix? This is A phi j phi I. This is, so to speak, can be viewed as the above equation for the eigenfunction phi I. Now for the specific test function, phi j, for the specific test function phi I. That means I get lambda j, phi j, and now the test function phi I. But now I use the orthogonality, saying this is lambda j times the Kronecker delta. That means only at the diagonal positions I have entries in this matrix, and the entries are just the eigenvalues. So the problem on solving the set of equations has vanished. I just have to divide by the eigenvalues. The whole work is now here in this case transferred in the computation of the ansatz space and the basis functions. This is then called a spectral method here, and we can also combine that with finite element methods and so on. It's a Galerkin method, but not a finite element method. So now we want to go a little bit in the general analysis of the finite element method. And we know already for convergence we usually have to have two basic ingredients. This is consistency and stability. And the interesting thing here, and we have seen with the finite difference method, the big problem is the stability. We have seen that if the matrix gets special structured, that it turns out to be an M matrix, then we have means to ensure the stability in a discrete L infinity norm, but in general, we do not know too much about that. So let's see how this is here in the finite element case. And to maybe before I start, I make a few remarks. Hopefully not too confusing. To point out again what is the difference between the finite difference method and the finite element method. So to speak, on philosophical grounds. That it might be, the finite element method is much, much more general, but it might well be, as we have seen, that in special situations they meet, that then the same discrete problems comes out. So what is, so to speak, our general problem? So what do we have to have? What we want to solve is an operator equation. So we want to solve something like, what is my notation? Yeah, AU equals B. Okay, it's not so, this notation should not be so unfamiliar, but here we need, of course, U is now not a vector, but a function. And what is this operator A? If we look at it in the pointwise sense, then that would be something where the Laplace operator would, for example, be come up. Here we would come up with the right-hand side and the boundary condition. So here we would have to have something like A being an operator composed of the Laplace operator. And so classical, let's say classical, in the classical setting, how should this be? So A would be from a function space V to W. And how could we do this? V could be something like C2 of omega, and we would like to have functions which are continuous up to the boundary. And okay, and what would be the second part? That would be where we end up. That would be something like continuous functions or L2 functions, and we need then something for the boundary condition, something like continuous functions on the boundary. And the operator, what would it be? It would be, say, minus Laplacian for the PDE, and let's say evaluation of the solution at the boundary for the ODE. That's just, yeah, doesn't help us too much now. It's just writing down what we said already. And then the discretization. The finite difference method. That would be something at the end of the day, a set of equations of this type. So, how it is in the weak formulation? In the weak formulation, we have something like AUV equals BV for all f aus V, and we are looking for a U from V which satisfies this equation. Now, where is this is again equivalent with something like that. Namely, how do I have to find and between how do I have to define my A now? Maybe we write it from we read it a little bit from the sorry, this is not necessary. We read it a little bit from the right hand side. So this is an equation for each V. This is a scalar equation for each V. Number equals number for each V. But we can, of course, also say this is an equation for a functional. A certain functional, a linear mapping from V to R, must be something. So this B is this B here. Okay, then necessarily, what should then be A applied to U? Necessarily, A applied to U is then this thing here. That's exactly what stands here. First question, is this also a linear functional? Answer is yes, because this is a bilinear functional here. So A of U is from the dual space of V as V is from the dual space of V. Okay, what properties has the operator A? So now this is A is now an operator from V to V star. What is it? It is linear. In the same way as we have linear operators here, we are only dealing with linear problems at the moment. It's linear because the A is also linear in this component. And so purely algebraically formulated, we have here by this defined an operator that is our operator equations. But now we are dealing with operator equations which have their values in dual spaces. And out of the sudden, this very strange concept of the dual space gets its natural meaning. Okay, and what is our discretization? What is now our discretization here, Galerkin, is that we are looking for a UH from VH such that A UH VH equals BVH for all VH from VH. Yeah, that's exactly the same thing. This is now again an operator equation. And now I'm so bold in using the same notation I use here. How do we call this guy? BH. And how is this? AH. Yeah, it's exactly the same thing as here. It's from VH to VH star. Same definition as above. And what is the BH? This is just the B restricted to the VH. Now we are here again in a finite dimensional situation. That is, we can, of course, as we did it already, represent the unknown function by a given basis and work out conditions for the coefficients in this basis. That's exactly what we did, leading us to the stiffness matrix. So what now has the stiffness matrix to do with this AH? And I only maybe tell you that, and you can work this out in the exercises. There is a good application of linear algebra where you did all this thing. In linear algebra, you introduced the representation matrix, the Darstellungsmatrix of a linear operator. At the moment, we are only dealing about algebraic structures. We do not have said that the A is continuous or whatever, or that the B is continuous. We're only dealing about a linear functional, and these are only linear structures at the moment. We will later on see that we need a little bit more. So, if I look at the representation matrix why I am entitled to use here the same notation. This is, in principle, this is something different. This here is a matrix. Firstly, this is a right hand, this is a vector. And this is, at the moment, something different. This is a linear form, and this is a linear mapping between the space and its dual. What is the representation matrix of AH? Now I have to specify the bases. I have to specify a basis in VH. Of course, there I take the basis with which I work. Let's say the nodal basis. That is the basis of VH. And now I need a basis. And now I need a basis, let's say psi1 to psi m, a basis of VH star, of the dual space. Okay. What kind, if you have to select a basis of the dual space, having given a basis of the underlying space, what would you take? Or what do you know? What is a possibility for a basis there? Something what I'm absolutely sure, maybe the engineering students are excused, but the mathematics students, 100%, cut off my right hand if you have not done that in the linear algebra. What is the construction to get from a base? You have a finite, we're talking now about finite dimensional spaces, of course. We're talking about linear algebra. You have a finite dimensional space, you have a basis, you have its dual space. How you get a basis there? What is the notion I'm asking for? Just tell me the name. At the moment, I'm still not willing to believe that your knowledge in linear algebra is close to zero. Very close to zero. It's a dual basis. I take here the dual basis to phi I. So how is the dual basis defined? So I have functionals to define. I know I can define those functionals if I just define them on the basis. Linear extension principle for linear mappings. So I have to say what this guy is on this guy here. And what should that be? Of course, this one here. That is the definition of the dual basis. And I'm 100% sure that you have seen that. Okay, so all this comes together. If I now take, in this sense, what is the representation basis? Of course, I haven't said it. It's just A, phi j, phi I. It's the stiffness matrix. Okay, so we should keep this a little bit in mind, that we are really working here in an appropriate functional setting, and the functional setting at the end of the day means if I say we do it variationally, it means we are working in a dual space. Okay. So now let's say what we can prove. So what we want to do is, and that is now everything much easier than in the finite different method. What we want to do, we want to compare our approximate solution, the solution from the Galerkin method, UH, and the exact solution of the variational problem. It's now no problem to look at this difference because they are all in the same big function space VH. They're in V. They're in V, but of course not in VH. But what we can do is now we can, so to speak, subtract. We have it here on the blackboard. If I'm free to choose here my test functions as long as they are in V. So I just take this finite dimensional space. So the test function only from VH here. Then I can subtract this equation from this equation. The right hand side goes away. And I get an equation for a function E, namely the difference of U minus UH. It's just the error function. That is the function which I want to estimate in a certain norm, where the norm should go to 0 finally. And I get this equation. AE V equals 0 for all V from VH. Okay, now this is an equation for the error, the so-called error equation, Fehlergleichung. Okay, now in our example, later on we will have general situation, but in our example, what properties does the A have? It is symmetric, bilinear, it's always bilinear, but it's in addition it's symmetric, and it's definite. So it produces a scalar product that we have used already. We have used already the norm coming from this scalar product. And what does that mean? That means in this specific A scalar product, the error is orthogonal to the space VH. And therefore this is also called the orthogonality relation of the error. What does that tell you? In which situation you have that the error is orthogonal to a space in which you want to approximate? Okay, I draw you a picture and you tell me what this has to do with what we are doing. The picture is not too complicated. The picture is in R2. R2 is, so to speak, our space V. This is a one-dimensional subspace. This is, so to speak, our space VH. This is the point. This is one of the points, and this is another of the points. Now you relate these 2 points to our notation and tell me what this has to do with that. So we have 2 guys. We have U and UH. Who is U and who is UH here? Only 2 possibilities. Select one. Who of these 2 is U and who is UH? What should I write here? U. Okay, and then we take UH here. Okay, that's right. U is in the big space, 2-dimensional. UH is in the small space, 1-dimensional. Okay. And what now has this picture to do with this statement? That's an orthogonality statement. It says in the A scalar product, the error is orthogonal to VH. Where do I see this here? What is here A? This picture, which scalar product I'm talking about? In this picture, I have tried to make this really orthogonal. What is this vector here? Actually, to be more precise, these are points. This is a vector in terms of affine geometry, but let's ignore that for a moment. So, what is this here in our notation? E. Let's say E or minus E. It's the vector I have to add to U to get UH. So, what do we want to have? U minus UH. So, this is E here. What does it say? This vector is orthogonal in the Euclidean scalar product here to the space VH. So what we are doing here is orthogonal projection in this case. We are looking for the point in the ansatz space which has the closest distance in the underlying norm we are dealing with. Now, of course, we are dealing not with the Euclidean norm, but with the A norm, induced from the A scalar product and in an underlying infinite dimensional space. But of course, we approximate in a finite dimensional space, otherwise it would also not make too much sense. But it's exactly this picture. So now we see what we can do with it. So, okay, this is stated here, and this tells us, and I think now I'm a little bit more careful with my right hand, but I would say, at least I would hope that you have seen this in linear algebra, that there's an equivalency between looking for the element of the smallest distance in a norm induced by a scalar product, and the condition that the error is orthogonal to the space on which I'm projecting. Therefore, this is called the orthogonal projection. And that's again here the statement. I have a subspace in some general vector space with an underlying scalar product. That's important, that's a scalar product. I have the induced norm. Here I measure the orthogonality. Here I say I want to have the element which has the smallest distance to the space. So to speak, the point is, in the moment I'm going to say, I want to have my approximate solution in the space VH, because these piecewise linear functions are pretty nice functions, so I would like to have an approximate solution there. The best thing which I can get, of course, is this here. That's the absolute maximum I can get. And the amazing thing here is, at least in this specific case, for a bilinear, definite bilinear form, I get this by the finite element approach. Okay. I skipped the proof here. Maybe you can read this if you have not yet seen it already. And now we want to generalize this a little bit. So we would like to give up the symmetry of the form, and we would like to give up the definiteness of the form. And we can and have some other assumptions. So now we are looking to a general situation, and now, so to speak, continuity, topology comes in. We require two things. So what is the situation? We have a bilinear form, it's called A, as till now, and we have a certain norm on the space V. This we had up till now also, but we had this identity. The norm was the norm induced by the bilinear form, as the bilinear form was even a scalar product. Now it's not a scalar product anymore. So what we require now two things for the bilinear form and the norm. First of all, we require that the bilinear form is continuous with respect to the norm. And now I'm not sure, some of you or most of you have already heard, I think, functional analysis, at least from there, or maybe from analysis or wherever. You should know that for a general nonlinear function, continuity at some point is a very local condition. Of course, if a function is continuous at one point, it doesn't need to be continuous at another point. That is different for linear function. If a linear function is continuous at one point, it's continuous at every point. And this again is equivalent with a much stronger requirement, namely, so if I have a linear function, let's say a linear operator phi between some vector spaces phi and v, and they are normed. So I have some distance where I can measure, and I'll take do not write an index here. I have normed spaces, so I can speak about continuity, and then I know phi is continuous everywhere, or at x equals 0, that's all equivalent, if and only if phi is bounded. What does that mean? That means it exists a constant such that I can estimate the norm of the images by the constant times the norm of the pre-image. That is a bounded map. This is a bounded mapping. So boundedness and boundedness and continuity is the same for linear mappings. What we now have here is a bilinear mapping, and for bilinear mapping, That's basically the same proof. For bilinear mapping, continuity is equivalent with this requirement, that there exists a constant such that AUV, modulus of it, can be estimated by this positive constant times norm of u times norm of v. Okay, let's go back to this special case where the norm is just the induced norm of A, as in the case where A is a scalar product. What kind of M can I choose then? For which M, or what is the, give me a hopefully good M for which then this condition holds true. So the scalar product is estimated by some constant times norm of u induced by the scalar product times norm of v. Give me an M. And tell me how this inequality is called. Cauchy-Schwarz, yeah, that's right. And what is the M? 1. Okay. So in this sense, this is a generalization what we require. And furthermore, so for example, the zero mapping would of course fulfill this requirement. But for the zero mapping, we wouldn't have very much of a PDE. And to get the specific type of PDEs what we have, we use a further property, and that is then called V ellipticity, V elliptisch, or V coercitivity, or coercivity. There are all kinds of versions. So we will call it here V elliptic. What does V elliptic mean? It's quite similar in the other direction. That means there is some positive constant alpha, such that now the quadratic part, AUU, can be estimated from below by alpha times the norm u squared. And again, if this is the induced norm, then of course this is trivial with alpha equals to 1, and that's an identity here. So these are the two requirements with which we will work now. And the first thing is, what we can see is that the finite element method has an inherent stability. We don't have to deal about stability. That is the amazing thing here. In the sense that we will see in a second, that is exactly the notion of, or very related to the notion of stability we have used up till now. We can estimate the norm. The norm is always the underlying norm now. We can estimate the norm of any solution by the constant 1 over alpha times a norm of B. This norm of B is now the operator norm of B. That means here implicitly is here now the assumption that B is not only a linear functional, but it's a continuous functional. We just said continuous is equivalent to boundedness, and boundedness just means that this number here is a finite number. That's just the boundedness. You see, the boundedness constant here is just an upper bound of this set here. So we can read in this case, if B is in addition not only a linear but a continuous functional on this underlying space V, then we have a stability in the sense that we have a global bound of all the solutions independent of the H. So it cannot happen that the solutions explode. So let's prove this. And the proof is very, very simple. Okay, so how do we deal with variational equations, with equations with values in dual spaces? We just select properly our test functions. And here we select as a test function the solution itself. So that's here. Now by the V ellipticity, I can estimate this term from below by alpha norm squared. And this I can estimate, obviously, that's an equality here actually, by this term here. And now I can estimate this term by its supremum. And that's it. And I see actually I've proven a little bit more. I've proven I can take the operator norm not of B but of BH, in the sense I've defined it here, namely the B restricted to BH, because we only have elements of VH here. And then the norm of the BH is then again in the situation that B is continuous, can be estimated by the norm. And okay, maybe I leave that here as it is. Now, okay, why is this related to the same stability? Is this more or less the same stability notion as we had for finite difference method? For finite difference method, we ended up in the discrete world directly here, and we said we have stability, or stability means that the inverse of the system matrix here in the chosen norms, in the corresponding induced norms on the matrices, is bounded by a constant independent of H. Now, maybe I say it very quickly, because the time is running. Let's go back to the assertion. If I look at this equation here, now we are in a situation where this equation is uniquely solvable. So I can also substitute the UH by an AH to the minus 1, the inverse of this operator, times BH. That means, and here I said I can substitute that by the norm of BH. That is, I can estimate, I have, so to speak, then a bound on the constant in the boundedness condition for the operator AH. And the bound is 1 over alpha. So equivalently, I can write this relation as AH in the induced norm to the minus 1 is estimated by 1 over alpha. And now I only have to relate this AH to a matrix AH, but this we at least stated already. That's actually a representation matrix. And that actually our stiffness matrix is the representation matrix. So it's very close to what we did after now. But it's in one functional framework. We don't have the one world and the other world, and we don't know how to relate them to one each other, to the other. And now, okay, about the approximation. In the scalar product situation, we have seen that the optimal situation was there. We had the orthogonal projection. We cannot do better. Okay, what do we have to have here? We have something which is basically the same thing. That's the so-called lemma of Serre. And it states we can estimate the error in the norm of the underlying space by the minimal error. So if this would be equal, then we would be in the same situation as before. But the minimal approximation error, so the minimum which I get if I look over all these norms, differences between U and any choice from VH. But I have to pay a little price, or maybe a big price, and then you have to multiply with m over alpha. Okay, so now let's first discuss a little bit this result. Is this good or bad? On the one hand side, one could say that's a very, very good result. Because what I want to know then later on, or the only thing what I have to do then later on, is to know how this approximation error is. How good can I approximate a function, any function of certain properties, by those ansatz functions which I have chosen. And then I get an h square here, for example, constant time h square, and the only thing what happens is these constants maybe get a little bit larger, that's all. So if I get an order of convergence here for this term, then I preserve this here. So in this sense, it's a very, very good result. But there might be situations where it's nevertheless problematic, namely, what could happen? Look at this number here. What could happen here with this number? Depending on the problem. This is a number which comes from the problems. It has nothing to do with the discretization. That the nature of the underlying PDE problem tells you how large the m and the alpha is. And it might well happen that either the m is very, very large, or the alpha is very, very small. And we will see later on in problems with convection, which are convection dominated, the alpha becomes extremely small. That is, we get here an astronomical factor here. That does not mean that anything is wrong from this order of convergence estimate, but it means that maybe we are never able to see it, because we cannot compute with such small h's such that the term which comes from here dominates the term which comes from here. And this is then really a problem, and that is the situation where we have to change this ansatz to get appropriate methods for convection-dominated problems. So let us first show now this lemma of Searle. So again, a simple proof. Okay. So we said we have the error equation that A applied to the error and some element of the discrete space gives 0. Sometimes one still calls this orthogonality. Of course, this is not quite correct because we don't have a scalar product anymore. Then one would just need this equal to 0 condition. So we can have here any element of the discrete ansatz space. In particular, I can write this arbitrary chosen element as UH minus some V. So let's do that. And we want to have an estimate for this quantity, U minus UH. Because of the V ellipticity condition, it's sufficient to deal with this term here. Okay, now we add this term. It's just a 0 what we are adding here. We put it together in the second variable. The UH drops out. And instead of the UH, we get here the general V. So in the comparison of the error here, we have changed this difference from the specific discrete solution to a general element without changing anything. That is just the orthogonality of the error. And now we can estimate further on. Now we can estimate this term now with a continuity. Continuity constant times norm U minus UH, norm U minus UV. One term here cancels. And then we have alpha times the term we want to estimate, less or equal than m times U minus V for any V from VH. And it means in particular also the infimum of those numbers. So the best approximation error in this space. So the factor we get it from is m over alpha, as we have seen. Okay, the discussion I've done here already. Now let's look again to our specific example. So we have our basic space V, either with this non-so-correct definition or with the correct definition where we do not yet know how to bring in this zero boundary condition, and we have our ansatz space with the piecewise linears. We have our linear form, and we have our B. So for the right-hand side, we assume that the f is an L2 function. This assures us, as we will see in a second, that the functional becomes a linear, not only a linear but a continuous function. So let us now check the properties. We are now in a situation that the A is also a scalar product. But that is not, so what we could do is we could use just the norm induced of this scalar product, and all the constants would become 1, as we have discussed already. That would be one possibility. Another possibility would be to use as a norm on our ansatz space, which is basically at the H1 omega space, we use this norm here. So we have this part here with the gradients, and we have this part with the function. So let's see what do we have to know that now all conditions are fulfilled. The first thing is we need continuity. Continuity is still easy. AUV can be estimated here Cauchy-Schwarz, now for this scalar product with the A, by A norm of U times A norm of V. But the A norm can be estimated by the 1 norm. There's only one non-negative part. In addition, so we have this trivial estimate here. So the continuity does not produce any problems. The problem now comes up with the V ellipticity. So what we would like to do is we would like to estimate the quadratic part, the AUU, that means the A norm of U squared, by some constant, positive constant, and the 1 norm of U squared. Is this possible in general? So what do we have? So here we have only the gradients. Here we have the gradients and the function. Is this possible for, say, a smooth function without taking into account the boundary conditions? Let's think of a smooth function. What about the function constant 1? What happens with constant 1? What do I have here? Let's take the function constant 1. 0. And what do I have here? Something. The gradient contribution goes away, but of course the L2 function of the 1, so I have basically area of the domain, square root of the area of the domain, which comes out, that is something positive. And that means I cannot do that. I need to have the boundary conditions, the fact that I deal with functions which are 0 at the boundary. And this is stated in the so-called, which I'm not going to prove now, which will be maybe in the exercise, the so-called Theorem of Poincare, which states the following. If I have an open-bounded set, then there is a constant only depending on the domain, not on the functions, such that I can estimate the L2 norm by the constant of this L2 norm of the gradient. And again, we see for the constants, for the functions not including the boundary conditions, of course, this is impossible, because here I have a 0 then. But the Poincare lemma said, as long as I have the 0 boundary condition, this can be weakened. I only need the 0 boundary condition to the part of the boundary, and there are further variants of that. I can assure that. And if I take this for granted, then I can now, so to speak, fulfill this requirement. Because I just subdivide here my norm into two parts. The one I leave it as it is, and the other one I estimate with the L2 norm of the function itself, and so I get my alpha. So I could, for example, choose the alpha in this fashion here. Yeah, what do we have now in this situation? We have now, on the one hand side, the coercivity. We have just ensured by taking advantage of the homogeneous boundary condition. And on the other hand side, we have this trivial relation between the A norm and the 1 norm. That means I have a situation, I have two norms. I can estimate positive constant of one of the norms by the other norm, and I can estimate the other norm by positive constant and the first norm. That means these two norms are equivalent. They produce the same notion of convergence. If I have a sequence convergent in the one norm, I have it convergent also in the other norm, and vice versa. The same for Cauchy sequences, boundedness and everything, which is related, so to speak, to norm. So here, this is really not a big difference in the sense whether I take this norm here and this. These are just two equivalent norms here, due to the boundary condition in this case. Okay, now let's go on. So we have seen stability, we have seen Sear's lemma, telling us there's only one task left. I missed one remark. Namely, we have to assure that the right-hand side is not only a linear functional, but a continuous functional. So this is our right-hand side here. And this we can, again, by Cauchy-Schwarz, we can estimate by the L2 norm of f. This is a finite number, as we have assumed. And the L2 norm of v. The L2 norm of v now can be directly estimated by the 1 norm of v, because this is L2 plus L2 of gradient, basically. And so we see the induced norm of v can be estimated by the L2 norm of v. So this would be, so to speak, a more specific form now of our stability estimate here. So there's one thing left, namely the estimation of the approximation error. Again, what is the approximation error? It's the error, the infimum about all possible differences between the one solution of the underlying variational equation of the U and elements of the untitled space. And of course I can estimate that by just, from the above, by just choosing any element of the untitled space. But I have to, of course, do this cleverly to choose this element. it has to do something. Of course, it has to do something with the norm, with the function I want to approximate. I could, for example, choose the 0. That would not help me too much, and I would get as an upper bound norm of u. Okay, that is nothing which goes to 0. So now I have to choose something which is in relation to the solution, which approximates the solution. And one possibility would be, as this specific element v bar, is to choose the interpolant. That the interpolant means we have a continuous function up to the boundary, 0 at the boundary, and now we take the interpolant in the space VH. That is, we take this uniquely defined element in VH which coincides at the nodal points. There's a little bit of a problem here, namely, of course, the continuity assumption here. We need this continuity assumption to speak of the interpolant. If we don't have a continuous function, we cannot evaluate a function at a point. For an L2 function, this doesn't make sense. Now we have to look at our definition of the spaces. If we take this preliminary wrong definition, that's no problem. Those are continuous functions. In the other situation with H1, we have a problem, because the H1 functions are in general not continuous functions. So what we could say is, okay, it must be not only an H1 function, but it must be additionally a continuous function. Or later on we will have another requirement which will assure us that the solution is a continuous function. So similarly to the finite difference method, we need then further regularity assumptions. But they are much, much weaker than those which we had to use for the finite difference method, where we had C4 or something like that. So in this we will prove later. In general, I only indicate what comes out. So this is first trivial. Of course, the minimum of all the deviations I can estimate by the deviation with the specific interpolant. And now I only have to estimate the error which the interpolant has. And it turns out that an estimate of this type here is possible. But this needs certain requirements of the triangulation, because we are not looking at one triangulation, we're looking at a whole family of problems. And for example, what is not allowed is that, basically spoken, that the angles, the minimal angle, gets smaller and smaller and smaller during this triangulation. And that also then means that the spider effect, which I mentioned, is not possible, that I get more and more neighboring points around a point. So these things are related to each other. So under certain assumptions, we can prove this estimate. And if we now put everything together, here's a little bit indicated what one really needs, but later on we will discuss this more in detail. So what now turns out, if we put everything together, what we have shown, probably not written down here in total, we have proven an estimate of u minus UH in the H1 norm. So this is quite a strong norm. It has function values and gradients, only in the L2 sense, so it's not directly comparable with the L infinity norm, but anyway, so this is the norm where we have the estimate. We need a little bit more than a weak solution. We've discussed this here, but not so much. And we have shown order of convergence, but only H here. So we have a basic and quite natural first order of convergence result, and of course now problems come up. Can we do better if we are not so, if we do not require so much in the norm? For example, what happens if we only look at the L2 norm? Can we get a better order of convergence? That would be one question. Another question, can we do something in the infinity norm? That is quite a complicated question for finite element methods. So these are questions we will deal with then in the general theory part. Okay, so next time we will go more down to earth and really think what ingredients are necessary to do a first basic finite element code.